All right, guys, Mr. Antonucci here, and in this video, we're going to discuss the fundamental theorem of calculus, which is a method for finding integrals more easily, and it avoids needing to use the limit of a Riemann sum. Now, the fundamental theorem of calculus is aptly named because it actually links the two branches of calculus, differential and integral calculus. And as it turns out, this theorem has two parts, each of which relates an integral to an antiderivative. So the first thing we're going to do is look at the theorem. Fundamental theorem of calculus is the first part. So we start by looking at, suppose f is a function on a continuous closed interval, a to b. The function capital I, defined by I of x, equals the definite integral from a to x of f of t dt. It has the properties that it's continuous on a to b and differentiable on the open interval. And the derivative of the integral is equal to capital I prime, which is the derivative of the integral, which is little f of x. So it's the integrand evaluated at x. Now, a couple of things to point out here is that this is actually a function because the upper limit is a variable. It's x, not an actual number. So what we're going to do is we'll actually look at an example here to understand each one of these based on this definition. So to use this, part A is basically saying just take the derivative with respect to x of the integral of 0 to x of the root of t plus 1 dt. This is actually no real work is needed here. We're just going to apply the theorem. And so this is going to be equal to the square root of x plus 1. Okay? Because remember, we're just differentiating the antiderivative, essentially. And so if we found the antiderivative of the square root of t plus 1, evaluated it at x, then took the derivative of that with respect to x, we'd be back at the original function we started with, but it would be in terms of x now. So similar with this one, the derivative here is equal to x cubed minus 1 over 2x squared plus x plus 1. Okay. The lower limit doesn't really matter because that is not going to affect our answer. And if you think about it in terms of antiderivatives, that's going to end up resulting in a constant. And then when you differentiate it, it's going to go to 0 anyway. So let's look at another example here. Where the upper limit is not simply just x. So we have to end up using the chain rule here where u of x is equal to 3x squared plus 1. Then we can think of this integral as y equals the integral from 4 to u of square root e to the t plus t dt. And then if we take the derivative of this, okay, so dy dx is going to be the derivative with respect to x of the integral from 4 to u of square root e to the t plus t dt, which is going to be the derivative of y with respect to u times the derivative of u with respect to x. This right here is where we're going to apply the chain rule. So we can think of this as the derivative with respect to u of the integral from 4 to u of root e to the t plus t dt. All of that times du dx. Now, du dx is the same as u prime. So u prime of x is 6x. So this all boils down to the derivative of the integral with respect to u, this part is just going to be square root e to the u, or plus u, times du dx. Excuse me, du dx. Okay? Now, we have to get everything in terms of x. So this is going to be e to the 3x squared plus 1, because it's e to the u, plus 3x squared plus 1, because it's e to the u plus u, times the derivative of u, which is 6x, so 6x. So this would be the entire answer. And notice, in terms of the original integral, if you look at the integrand, we basically plugged the 3x squared plus 1 in for t, and then multiplied by the derivative of that. So notice how it's plugged in for t here and here, and then the derivative multiplies. And that's essentially using the chain rule. Okay? So another example that we may come across is when the lower limit is a variable and the upper limit is the constant. So this is actually backwards because the variable must be the upper limit of integration. So we can use the property that if you flip the limits, you change the sign. So this could actually be rewritten as the derivative with respect to x of the opposite, the integral from 5 to x cubed of t to the fourth plus 1 to the 1/3 dt. Okay? And here, in this case, u is equal to x cubed, and u prime is 3x squared. So we could actually rewrite this in terms of u. So if we let y equal square root, or excuse me, the integral from 5 to 5x cubed of t to the fourth plus 1 to the 1/3 dt, and let u equal x cubed, then we could take the fact that dy dx is going to be equal to dy du times du dx. Okay, so um, we need the negative here. So by the chain rule, we're going to have the opposite of u to the fourth plus 1 to the 1/3 times u prime, essentially. And then we could plug in the u and the u prime. And you have negative x cubed to the fourth plus 1 to the 1/3 times 3x squared, which we can rewrite that as negative 3x squared times x to the 12th plus 1 to the 1/3 power. Okay? Now, it's important to understand that the differentiation is with respect to the variable that appears in the upper or lower limit. So with respect to x, the answer ends up being a function of that interval. Okay, so just be careful there because we have an x, we have a t, we have a u, but the limit of integrations variable determines what we're going to differentiate with respect to and what our answer is going to be in terms of. So here's another example where we have two different functions, f and g. So f is defined as an integral. And notice a couple of things. The upper limit is x, or excuse me, 6x, so it's a variable. And g of x is a composite function. It's f of cosine x. So getting kind of crazy here. So if we find f prime, okay, so f prime of x is equal to the derivative with respect to x of the integral from 0 to 6x root t squared plus 1 dt. In this case, our u is 6x, so u prime is going to be just 6. So the derivative here is, it helps me if I think of this as y equaling the integral from 0 to 6x of root t squared plus 1 dt, then dy dx is equal to dy du times du dx. So that's going to be square root of u squared plus 1 times u prime. Now, u in this case is 6x, so it's going to be 6x squared plus 1 times 6, which would give us 6 square root 36x squared plus 1. Okay? Now, for part B, g prime of pi over 2. Okay, so g prime is going to be equal to the derivative of f of 3 cosine x. So it's going to be f prime of 3 cosine x times negative 3 sine x. Now, I actually just did g prime of x, not g prime of pi over 2. All right. So this evaluated at pi over 2 is going to be negative 3 sine pi over 2 times f prime of 3 cosine pi over 2, which is going to be negative 3 times sine of pi over 2 is 1 times, now 3 cosine pi over 2, cosine pi over 2 is 0, so 3 times that's still 0, so it's going to be f prime of 0. Okay, now f prime of 0, this is f prime of x right here. We just figured that out in part A. If I plug 0 into that, I would have 6 times the square root of 1, which is just 6. So it's negative 3 times 1 times 6 gives us negative 18. And then the last piece says express the maximum value of f on the integral of 0 to pi, or an interval of 0 to pi as an integral, but don't evaluate it. So from part A, we can conclude, so here, the f prime is positive, greater than 0, for x less than pi and greater than 0. Because if you look at f prime right here, it's always going to be positive no matter what values you plug in, because x has to be between 0 and pi. When you square any of those, they're still positive. Multiply by 36, add 1, still positive. Take the square root, still positive, times 6, still positive. So, so f is increasing on this interval. So the max is at x equals pi, which is the right endpoint. And so that would be f of pi. Express that as an integral, it'd be the integral from 0 to 6 pi of square root t squared plus 1 dt. All right, guys, that's it for this section. Hope that was helpful to you. Make sure you reach out if you have any questions. Take care.